All right, folks, we're going to continue working here in Chapter 10. In Section 10.3, we're going to study infinite series, or as you'll soon hear, I'm just simply going to call it series. But here we go. If you have a sequence, A sub n, that's what we just looked at in the prior section. If you see, remember that's the sigma notation, if you see sigma n equals 1 to infinity of A sub n, that just means you're going to add up the terms of the infinite sequence. So the sum from n equals 1 to infinity A sub n, that equals A sub 1 plus A sub 2 plus A sub 3 plus yada 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 plus A sub n plus yada yada yada. Well, that's what is called an infinite series. Or quite simply, I'll just call it series. The A sub 1, A sub 2, A sub 3s, etc., they're called the terms of the series. And to determine the sum of a series, what we're going to do is we're going to begin by looking at a sequence of partial sums. So here's what a sequence of partial sums is. The first partial sum, denoted S sub 1, is simply the first term of the series, A sub 1. The second partial sum, S sub 2, equals the sum of the first two terms of the series, A sub 1 plus A sub 2. The third partial sum, S sub 3, equals the sum of the first three terms, A sub 1 plus A sub 2 plus A sub 3. And then I have a yada 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 in there, so that in general, the nth partial sum, S sub n, equals the sum of the first n terms of the series, or A sub 1 plus A sub 2 plus A sub 3 plus yada 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 plus A sub n. If the nth partial sum, that's S sub n, if it converges, then we're going to say the series converges. I'm going to put this into a definition. So for the infinite series, the sum of n equals 1 to infinity of A sub n. The nth partial sum is defined to be S sub n equals A sub 1 plus A sub 2 plus A sub 3 plus yada 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 plus A sub n. If the sequence of partial sums, as I'm using the sequence notation, converges to a number s, then the series from n equals 1 to infinity of A sub n converges, and we're going to call s the sum of the series. Moreover, we can actually write s equals A sub 1 plus A sub 2 plus A sub 3 plus yada 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 plus A sub n plus yada yada yada. We can write s equals the sum of the series. If the sequence of partial sums diverges, well, then the series diverges. So here's the deal, folks. When we are studying series, there are two really big questions that we attack. There are two big questions that we are asked, that we're trying to find the answer to. The first big question, does the series converge or does the series diverge? And then the second big question, if the series converges, what is its sum? Now, folks, neither question is easy, especially question 2. In fact, quite often, we're going to know that a series actually converges, but we don't know what its exact sum is. We could have an approximation, but we don't know its exact sum. We know that it converges, but we don't know its exact sum. So let's look at an example. Does the series, the sum of n equals 1 to infinity of 1 over 2 to the n, and the terms of that series would be 1/2 plus 1/4 plus 1/8 plus 1/16 plus yada yada yada, does it converge or diverge? And if it converges, well, let's see if we can get the sum, if possible. So I tell you what, write this down. I'm going to head off to the chalkboard to work through this example. All right, here in this example, we were asked, does the series n equals 1 to infinity, 1 over 2 to the n, and I wrote out the first 4 terms, does that series converge or does it diverge? And if it converges, if at all possible, let's see if we can determine the sum. First thing I want to mention about this infinite series, it actually has a name. It's called Zeno's paradox. Zeno was a dude, lived way back ancient Greek time, and he actually phrased the paradox a little differently. He phrased it as a race between Achilles and a tortoise. And he said that he could set it up so that the tortoise would beat Achilles and, say like a 100-yard dash. And so what he proposed was that he'd give the tortoise a 10-yard head start. So he'd put the tortoise 10 yards ahead of Achilles, and then when they say go, the tortoise takes off and Achilles takes off. He said that in order to try to catch the tortoise, Achilles would have to get to a point that was halfway to the tortoise. And then from that point, he would have to get to a point halfway to the tortoise. And then from that point, he'd have to get to another point halfway to the tortoise. And so he said not only would Achilles never beat the tortoise, he would never catch the tortoise. And that's why it's called a paradox, because he will beat the tortoise. He will catch and win the race. And that's what this infinite series is really all about. But right now, the only thing we can really do in trying to figure out whether or not this series converges or diverges is look at a sequence of partial sums. So I'm just going to start writing down partial sums. So the first partial sum, well, it's just the first term, 1/2. The second partial sum, well, it's the first term plus the second term. And I think 1/2 plus 1/4, that's 3/4. So the third partial sum, well, that's the sum of the first 3 terms. So 1/2 plus 1/4 plus 1/8. If I add those up correctly, I get 7/8. Okay, so now I'm wondering if I've noticed enough here to try to generalize and come up with a pattern for the nth partial sum. But let me write down what the nth partial sum would be. It would be 1/2 plus a 1/4 plus a 1/8 plus yada 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 plus a 1 over 2 to the n. That'd be really cool if I could come up with a formula for this. So for me, the key is looking at, let me start looking at the second partial sum and the third partial sum. So when I look at the second partial sum and the third partial sum, the first thing that jumps out at me are the denominators. It looks like this denominator of 4, that's 2 squared. 8, well, that's 2 cubed. So I can even look at the first partial sum. 2 is 2 to the first power. So let me just try to write out here that I've noticed 4 is 2 squared, and I've noticed 8 is 2 cubed. Now let's look at the numerators. This numerator is 1 less than the denominator. And that numerator is 1 less than that denominator. So it looks like 1 less than the denominator. Well, I'd have a 2 squared minus 1 there. This is 1 less than the denominator. Since the denominator is 2 cubed, the numerator would be 2 cubed minus 1. See in the pattern? The second partial sum, the third partial sum, exponents, I'm thinking, noticing that pattern. Remember in the last video, the last section, I said there would be something about being able to recognize a pattern. I think that can tell me that the nth partial sum will be 2, okay, let's keep the same, let's keep that exponent, 2 to the n minus 1 over 2 to the n. So we have the nth partial sum as being 2 to the n minus 1 over 2 to the n. So now how do we know if this series converges? Well, if the sequence of partial sums converge, then the series converges. So if we have the sequence of partial sums given by S sub n equals 2 to the n minus 1 over 2 to the n. S sub n is 2 to the n minus 1 over 2 to the n. To determine if that sequence converges, that's what we did in the last section. We need to do the limit as n goes to infinity. We need to do the limit as n goes to infinity of S sub n. Well, that's the limit as n goes to infinity of 2 to the n minus 1 over 2 to the n. So in finding this limit, I think I would make use of the fact that that's a common denominator. So I could write this as 2 to the n over 2 to the n minus 1 over 2 to the n. And we know 2 to the n over 2 to the n is 1. So now let's find the limit. The limit as n goes to infinity of 1 is 1. The limit as n goes to infinity of 1 over 2 to the n, well, that's 1 over an incredibly large number, that's 0. This gives us the limit as being 1. So the sequence of partial sums converges, and it has a value of 1. That tells us that this infinite series, 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1 over 32 plus 1 over 64 plus yada 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 forever and ever, it converges, and not only that, it has a sum of 1. That's what we just saw in the slides. That's what we were talking about, the sequence of partial sums. If it converges to S, then S is the sum of the series. So that's our first example where we actually had to look at a sequence of partial sums. In the grand scheme of analyzing infinite series, doing a sequence of partial sums is what some would refer to as being like the brute force method. We hope to not have to do this too often. Maybe this would be like the one time. But let's head back to the slides and see what's next. All right, hopefully we saw the importance of looking at a sequence of partial sums for that example. Remember that was I called it Zeno's paradox. Next up is a process that I just call cataloging of series. So in the rest of this chapter, we are going to learn somewhere around 10 different tests for analyzing series. I mean, they're going to have names, and this is what we're doing in the rest of chapter 10. A big key going forward is going to be recognition. Recognizing what the series looks like, and then use the appropriate test to determine if the series converges or diverges. So things that we're going to be hearing going forward and learning about will be, is it a geometric series? Is it a piece series? Is it a series that we could use the direct comparison test on, or the limit comparison test, or the integral test? Or should we be using the ratio test? Like I said, we're going to learn 10 different tests going forward in this chapter. One thing I want to point out, keep in mind, all we're doing right now is really arithmetic. We're basically just looking at adding up an infinite number of numbers. I mean, the series we're going to be looking at are nothing but numbers, and we're just adding. So it's basic arithmetic. With the kicker that we're adding up an infinite number of numbers, and we're trying to determine if there's an actual sum, which means the series converges, or if there isn't a sum, which means it diverges. Now, in the next chapter, we're going to generalize the arithmetic. That's what we're doing here, is the arithmetic. We're going to generalize it, and we're going to start to look at functions. So everything we're about to learn in this chapter, all of these different tests, all of them are going to be just very small little weapons that will be used in the next chapter when we start analyzing functions. So folks, with that said, the first quote test that we will look at is what is called a telescoping series. So in this example that we're about to do, we're going to see an old friend of ours, an old buddy, an old technique of integration that's kind of helpful in analyzing a telescoping series. So here's the example. Does the series, the sum n equals 1 to infinity of 1 over n times n plus 1, does that series converge or does it diverge? So what I'm going to do now is I'm going to head off to the chalkboard and let's work this out and see what the deal is. All right, now here we are beginning our cataloging of series, or what I like to call cataloging of series. And the first one that we look at is called a telescoping series. Excuse me. So you were asked, does this series converge or diverge? The series n equals 1 to infinity. Oh, by the way, folks, sometimes I just don't write the n equals here. It's just me being kind of lazy. 1 over n times n plus 1. And I went ahead and I wrote down the first three terms of this series. So this term is when n is 1. This term is when n is 2. That term is when n is 3. Yada, yada, yada. So does this series converge or diverge? And then I kind of foreshadowed that an old dear friend of ours was going to be helpful in this situation. And that's when I look at this 1 over n times n plus 1. I know 1 over n times n plus 1 can be rewritten as 1 over n minus 1 over n plus 1. Now, what did I do in order to come up with that? It's the old dear friend of ours that we learned in the chapter on techniques of integration. I cranked the 1 over n times n plus 1. I cranked it through partial fractions. I did a partial fraction decomposition on it. That's the old dear friend. So I'll save that for you to work out on your own to make sure that I'm not lying to you here, and I'm not. So partial fractions came in handy here. All that means, it means I can take my series and I can say, all right, another way to look at the series is, since 1 over n times n plus 1 can be rewritten as 1 over n minus 1 over n plus 1. And I could start to write down terms that, for this. I mean, if n is 1, we would have a 1/2 minus, if n is 1, we would have a 1 minus 1/2. If n is 2, we would have a 1/2 minus 1/3. If n is 3, a 1/3 minus 1/4, yada, yada, yada. And, quick check. 1 minus 1/2, that is 1/2. 1/2 minus 1/3, well, that's 3/6 minus 2/6, that is 1/6. 1/3 minus 1/4, that's 4/12 minus 3/12, that is 1/12. Well, we're going to go through the process of trying to come up with a formula for the nth partial sum. So going through this again. Partial fraction or partial sums. So we know the first partial sum is 1 minus 1/2. All right, the first term. The second partial sum is 1 minus 1/2 plus 1/2 minus 1/3. Well, hey, notice if I were to add these together, minus 1/2 plus 1/2, they'd cancel out. So that would leave me with just a 1 minus 1/3. Hey, that's kind of neat. The third partial sum, 1 minus 1/2 plus 1/2 minus 1/3 plus a 1/3 minus 1/4. Check it out. That's 0. And you have minus 1/3 plus 1/3. That's 0. So it looks like we're just left with 1 minus 1/4. It's looking pretty cool, isn't it? So what about the nth partial sum? Now let's see. The nth partial sum. Well, the nth partial sum, I'll write down some of these terms. 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4 plus yada 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 plus, so what would the last term be? Well, 1 over n. 1 over n minus 1 over n plus 1. So here's what I'm looking at. We know those cancel. We know those cancel. In my yada yada yada, would there be something that would cancel out the minus 1/4? Yeah, it would be the first number in the next group. So that would cancel out. And I think you're seeing all these terms in the yada yada yada, they're going to be canceling out. But the real question is, will anything in that last grouping of the nth partial sum cancel out? And it's in this very last term, there would be something that would cancel. There would be a minus 1 over n that would cancel with that 1 over n. So look at what we have. And I'm going to pull it up over here because I'm running out of room. We have S sub n equals 1 minus 1 over n plus 1. S sub n equals 1 minus 1 over n plus 1. So just like in the last example, when we looked at Zeno's paradox, we had to come up with a formula for, the nth partial sum. Now we want to see, does this sequence, for the nth partial sum, does it converge or diverge? And the way we know if a sequence converges or diverges is we take the limit as n goes to infinity of S sub n, so that's 1 minus 1 over n plus 1. And the limit as n goes to infinity of 1 is 1. The limit as n goes to infinity of that term is 0. So the sequence of partial sums converges. It has a value of 1. That tells me that the series 1 over n times n plus 1, it converges. And moreover, it converges and it has a sum of 1. So that's a telescoping series. And it's given the name telescoping series because of all this canceling out stuff. It's like everything cancels out except for maybe like a first term and a last term. So everything cancels out, it collapses down. That's why someone decided to call it a telescoping series. But the key in doing it was to look at a sequence of partial sums. So that was the key. I have something I'd like you to read in the book. In the book, I'd like you to read example 3. Example 3 in the book. There are two parts to example 3. There's a part A and a part B. There are examples of telescoping series. I believe part A involves a trig function. Yeah, just don't get freaked out by it. And I think part B starts off with something that they show you how you can change your indexing. So when you look at part B and they change the indexing, remember this is the indexing, they changed it. Look at how they changed it, and they end up changing it, and they come up with a series that looks exactly like what I have here and what this example is. So the first one in our catalog, telescoping series. So let's head back to the slides and see what's next. All right, now that we've seen what a telescoping series looks like, and why it's called a telescoping series, because when we start to look at partial sums, terms cancel out, so they kind of collapse down. We're ready to look at the next in our catalog. And the next in our catalog, the next type of series we're going to look at, well, it's called a geometric series. Okay, what I find really neat, really cool about a geometric series is not only are we going to have a test on determining if the series converges or diverges, and we'll know it real quickly just by looking at the series. We're going to be able to immediately know if it converges or diverges. But we're going to develop a little formula so that if it does converge, this little formula will tell us what the sum is. And I think that's kind of cool. But first, let's define what a geometric series is. So this definition, the series given by the sum n equals 0 to infinity, a r to the n. And I wrote out some of the terms of that series. So the first term would be a, then you'd have plus ar squared plus ar cubed plus yada 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 plus ar to the n plus yada yada yada. That's a series that's called a geometric series with ratio r. So that r is called the ratio of the geometric series. And here's a theorem. A geometric series with ratio r, it diverges if the absolute value of r is greater than or equal to 1. The geometric series with ratio r, if that ratio r, the absolute value of it, is between 0 and 1, then the geometric series converges. So it's all about that ratio r. If the absolute value of the ratio r is greater than or equal to 1, it diverges. If the absolute value of the ratio r is between 0 and 1, then the series converges. So we'll be able to know immediately converge or diverge. And if it does converge, its sum is given by the formula s equals a over 1 minus r. This is really, really cool. In fact, it's so cool, I think we need to prove this theorem. This is something that we just have to do because it is so cool. So to prove this theorem, I'm going to head off to the chalkboard and work through the proof. All right, next up in our cataloging of series, we saw the geometric series. The geometric series, this is number 2 in our list. Geometric series is really important. It's extremely important. You need to know geometric series. You need to know it by name. You need to know what it looks like. You need to know when it converges, when it diverges. And so I've kind of briefly written over here, this is what a geometric series looks like. And I wrote out some of the first few terms, a plus ar squared plus ar cubed plus yada 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 plus ar to the n plus yada yada yada. I ran out of room for the last yada, but you know it continues on forever and ever. And then our theorem said that if r, the ratio, if the absolute value of r is greater than or equal to 1, the geometric series diverges. If the absolute value of the ratio is between 0 and 1, the geometric series converges. And I said we were going to prove this. We're going to prove it because it's kind of astonishing that it's a series, it's a family of series, and it's an important series, that we have a formula that tells us the sum. In fact, we know the formula. It was in the theorem. S equals A over 1 minus R. So let's work through the proof. Proof is going to start off by looking at the nth partial sum. Okay, so now let's just come over here and look at this. I need you to understand something about exponents. If I ask you for the second partial sum, that would be A plus AR. If I asked you for the third partial sum, that would be A plus AR plus A squared. The fourth partial sum, A plus AR squared plus AR cubed. You notice on each of those partial sums, the exponent is one less than what the actual partial sum is. Third partial sum, the sum of these three terms, third partial sum ended with an exponent of 2. Fourth partial sum, sum of the first four, ended with a term, the exponent is 3. That's one less than the partial sum. That means the nth partial sum is A plus AR squared plus yada 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 plus AR. This exponent has to be one less. So it's AR to the n minus 1. You know, rarely do I do this, but I'm going to number this equation. So let me call this equation 1. All right, so now just for fun, it's kind of important, but for fun, I can multiply both sides of this equation by r. So let's multiply both sides by r. If we multiply both sides by r, we get r s sub n equals, so each one of these terms gets multiplied by r. So we'd have a times r plus ar squared plus ar cubed plus everything in the yada 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 is getting multiplied by r. And now this gets multiplied by r. So when that gets multiplied by r, that gives me ar to the n. Remember, it's an old property of exponents. When the bases are the same and you multiply, you add the exponents. So when this gets multiplied by r, that's r to the first, n minus 1 plus 1 leaves me with an n. And I'm going to number this equation. It's equation 2. So here's what we're going to do next, a little subtraction. We're going to subtract, I'll write this in here. We're going to subtract 2, equation 2 from equation 1. So if I take equation 2 and I subtract it from equation 1, on the left side here, I'm going to get s sub n minus r s sub n. On the right side, I'm going to get, let me write it out, a plus ar plus ar squared plus yada 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 plus ar to the n minus 1 minus ar plus ar squared plus ar cubed plus yada 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 plus ar to the n. So that's subtracting equation 2 from equation 1. Okay, it looks like a mess. Bear with me. Over here on the right side, we can factor out an s sub n. So let's factor out an s sub n. That leaves us with 1 minus r. On the right side, let's do some cleanup. Let's combine any like terms we can. I mean, notice, well, we have an a. But we have an AR minus an AR. Gone. AR squared minus AR squared. Gone. The next term here would be AR cubed minus AR cubed. Gone. AR to the n minus 1, I think that would be the term that would appear right here. Right before this plus sign would be an AR to the n minus 1. We cancel out with that term there. So look at what you're left with. You're just left with, on the right-hand side, an A minus AR to the n. Well, that looks pretty nice. Things have collapsed down nicely. In fact, on the right side, seems like a logical thing to do next is to factor out the A. Okay, now after we factored out the A, you know what? We can divide both sides of this equation by 1 minus r. That gives us, here it is, a formula for the nth partial sum. Now I'm going to rewrite this. I'm just going to kind of, running out of room, just going to kind of pull it here. I'm going to rewrite this as two fractions. I'm going to multiply it as this right side. I'm going to multiply it as two things being multiplied together. Two fractions, if you will, being multiplied together. The first one is A over 1 minus r. And then the second fraction would be 1 minus r to the n over 1. Well, I'll just write that as 1 minus r to the n. Alright, so here's the deal. If r is between, I'll say the absolute value of r, if it's between 0 and 1, so if r is, say, 1/2 or 1/4 or 7/8 or 15 over 23, just somewhere between 0 and 1, as n heads off to infinity, think about this, r to the n. So think if that r is a number between 0 and 1. Let's make it a friendly number. Let's make it 1/2. 1/2 to the n power. As n heads to infinity. Well, as n heads to infinity, 1/2 to the n would be getting closer to 0. So as long as r is any number between 0 and 1, as n heads to infinity, r to the n is heading off to 0. So when we compute the limit as n goes to infinity of s sub n, that's the limit as n goes to infinity of a over 1 minus r times 1 minus r to the n. I mean, all this stuff right here is just a constant. We just analyze that as n goes to infinity, this is 0. 1 minus 0 is 1. We get the limit to be a over 1 minus r, which is, because we just did the limit of the sequence of partial sums, that means this expression gives us the sum of a convergent geometric series. I thought we needed to look at this proof because it's kind of astonishing that we have a formula that will tell us the sum of an infinite series. A little formula, a over 1 minus r. So that's it for the proof. Thanks for indulging me on that. That's something I think is just remarkable. So let's head back to the slides and see what's next. I bet we look at some examples of geometric series. But let's head back to the slides and see what's next. All right, now that we've seen the proof of the theorem there for geometric series, let's do an example here. Okay, so do the following series converge or diverge? And if I don't always say this, we need to state a reason for our answer. You'll see as I work through how I will represent the answers. So here are two series, part A and part B. So you know what to do. Hopefully you're getting into the groove of things. You know to write these down because I'm going to head off to the chalkboard and work through them. All right, in this example you were asked, do the following converge or diverge? And state a reason for your answer. And this is one of the things, the question, does something converge or diverge? We could flip a coin. If it comes up heads, we'll say converge, tails, we'll say diverge. And we have a 50-50 chance of being correct. It's the state a reason for your answer. I pay particular attention to that. So this is the first series. The sum from n equals 0 to infinity, 4/3 to the n. Oh, by the way, one more time. For whatever reason, your book likes to use k's. It's like the only book I think I've ever seen that does that. I'm using n's. So here's the key. Mentioning recognition, you have to recognize. You have to start to be able to recognize what these series are. First thing that jumps out at me, I see a 4/3 to the n. 4/3 to the n. This is geometric. A is 1, R is 4/3. So I would write down, first thing I would write down, this is a geometric series. The ratio is 4/3. Notice that that is greater than 1. That means the series diverges. That's it. This is stating a reason. Telling me what test you're using, what part of it, and your conclusion. So let's look at B. The sum n equals 0 to infinity, 3/2 to the n. Well, when you've been doing this too many years of your life like me, you immediately see that's geometric, but you have to maybe kind of do some manipulations to see that it's geometric. So what do I mean by that? Well, first, 3/2 to the n can be rewritten as 3 times 1/2 to the n. Second, that old rule of exponents, 1/2 to the n, that's the same thing as 1/2 to the n. Now I see it is a geometric series. A is 3, R is 1/2. So now I see this is a geometric series. The ratio R is 1/2, which is less than 1. Therefore, the series converges. Moreover, we could find the sum of the series. We know to do A over 1 minus R, and that'll tell us the sum of the geometric series. So I want you to practice a couple of them here. I want you to, in this section, section 10.3, I want you to do numbers 29 and 37. I think the book asks you to find the sum of the series or state that it diverges. So let me just kind of modify that a little bit. First, determine if the series converges or diverges. Both of them better be geometric series. So determine if it converges or diverges. Do that first. Then if it converges, find the sum. Don't spend a whole lot of time on 29. I'll do it here at the board because there's something sneaky embedded in it. But 37, nothing sneaky about 37. So go ahead and do these two. Pause the video. When you've done those two, restart the video and I'll be here at the board working it out. Alright folks, here we are doing number 29, number 37. And I'm actually going to do number 37. I'm going to do that one first. Because 29, I have a lot of things I might want to babble about and I might need more room. So let's look at 37 first. Hey, the first thing you have to do is recognize pattern. and try to write it into series notation. So the first thing that I would say I notice is this, well, let me rewrite it. I mean, I could rewrite e over pi as e in parentheses with an exponent of 1, but e squared over pi squared is e over pi squared. E cubed over pi cubed is e over pi cubed. I think I'm seeing a pattern, so I could write it in the sigma notation. It looks like the sigma notation is just e over pi to the n. Now, the starting value for n. It looks like I am starting at n equals 0. Because e over pi to the 0 power would be 1. And then e over pi to the first power is e over pi. E over pi squared, well, that's it. Folks, that's a geometric series. We have a geometric series. R is e over pi. I don't know exactly what e over pi is, but I do know it's less than 1. And because it's less than 1, I know it converges. Then moreover, I could find the sum. I know the sum for a convergent geometric series is a over 1 minus r. A is 1. R is e over pi. And folks, I don't like the way this looks. I mean, I have a fraction, and in the denominator I have a fraction. So I could just multiply the numerator and denominator by pi to get pi over pi minus e. So geometric series, I wrote down what the r was, my conclusion it converges, and then I came up with the sum. So 37, pretty straightforward. 29. Okay, there's a lot going on here in 29. You have, first off, you have an e to the negative 2n. If you're thinking the first thing I would do is rewrite this so that I have a positive exponent, you are correct. So I would rewrite this as 1 over e to the positive 2n. Next, rule of exponents allows me to rewrite e to the 2n as e squared to the nth power. Next, a rule of exponents allows me to rewrite this fraction as 1 over e squared, the whole thing to the nth power. Now I see I have a geometric series. You know, this is the R. So we have a geometric series. R is 1 over e squared, which is definitely less than 1. So this converges. And because it converges, I can find its sum. And we know the formula is a over 1 minus r. But here's where things get a little tricky with this geometric series. That formula, a over 1 minus r, to find the sum of a convergent geometric series, it's only true for finding the sum if you're starting at a value of 0, n equaling 0. This is starting at n equals 1. So let's look at the difference. This is really, it's subtle, but yet it's pretty important. So I'm going to erase 37. And let me write down over here the original series. Let's list some of the first few terms of this series. So the first term would be, well, e negative 2 times 1 would be e to the negative second. And as 2, I'd have e to the negative fourth. e to the negative 6, e to the negative 8, yada, yada, yada. Now, what is the series if we start at 0? If we start at 0, the first term is, well, you put 0 in, the exponent 0, e to the 0 is 1. Then, when n is 1, we'd have e to the negative 2nd. And then we'd have e to the negative 4th, e to the negative 6, plus yada, yada, yada. The formula for the sum of a geometric series that converges, that formula is valid for when it starts at 0. Its starting value is 0. So we can find the sum of this series. In fact, let's do that. The sum of this series, a over 1 minus r. Okay, a is 1. R is, all right, let's see. Over here I have what r is. Oh, r is 1 over e squared. You know I don't like the looks of that. So I multiply numerator and denominator by e squared. This is the sum of this convergent geometric series. But we are being asked, what is the sum of this series? What is the sum of this series? Folks, what is the only difference between these two series? It's this term right here. That's the only difference. This series starts at e to the negative 2nd. This one started with 1. So if we know this series sums up to e squared over e squared minus 1, to get the sum of this series, all we have to do is subtract off that term, subtract off the 1. So we take the e squared over e squared minus 1, subtract 1. Which we might as well get a common denominator and get one nice little happy looking fraction. So we have e squared over e squared minus 1 minus e squared minus 1 over e squared minus 1. So we get a common denominator, make a happy fraction. Let's see, e squared minus e squared is 0, minus a negative 1 is 1 over e squared minus 1. So not only did this series converge, but we know that its sum is 1 over e squared minus 1. So folks, you have to be careful when using the sum formula. It only works when you start off at 0. That's the first thing for a geometric series. Second thing, you can do it and just subtract off however many terms you have to get the sum of the series in question. What's embedded here is a bigger point. Subtracting off or adding on a finite number of terms does not affect the overall convergence or divergence of any series. That's something to just kind of keep in mind going forward. So hopefully you at least got both of them, that you knew both of them converged. You're getting a little happier with the geometric series test. I think there's one more thing I wanted to look at on the slides, so let's head back to the slides and see what that is. Well, folks, there were a lot of things embedded in that example, that last example, and in the 2 homework problems that I asked you to do. So just to recap real quickly before I go on, you know, the formula for the sum of a geometric series, you know, that formula, S equals A over 1 minus R, it's valid if the geometric series has a starting value at n equals 0. So we saw that sometimes you have to modify it and do, you know, subtract off a term. So with that said, the next example that I want to look at is going to highlight, and I mentioned in one of the problems we just looked at, where a series actually begins. It's irrelevant on whether or not the series converges. This is equivalent to saying that the convergence of a series is not affected by the first few terms, or by removing a finite number of terms at the beginning of the series. And this example, we're going to prove that 0.9 repeating equals 1, as it's one of my favorite examples. So let's head off to the chalkboard and let's prove that 0.9 repeating is equal to 1. All right, this example, one of my favorites. Proving 0.9 repeating equals 1. There are many ways to look at this. I've shown people that really all they know is, say arithmetic and how to add fractions, that 0.9 repeating is equal to 1. You know what I mean by that? 1/3 is 0.33 repeating. 2/3 is 0.66 repeating. Well, if you add them up, on the right side, if you add all this up, you're going to get 0.99 repeating. On the left side, 1/3 plus 2/3 is 1. That's just using basic arithmetic. And then if someone knows algebra, a fact in algebra is that every number has a decimal, and every decimal number that terminates or repeats can be written as a fraction. Well, here's a repeating number. There is some fraction, I'll call f, that's equal to 0.9 repeating. And then I'd say, well, this is just a simple equation. Multiply both sides of that equation by 10. So you get 10f equals, and when you multiply this side by 10, you get 9.99 repeating. Go ahead and subtract. 10f minus f is 9f. 9.99 repeating minus 0.99 repeating. Everything to the right of the decimal point would cancel out. You get the fraction as 1. 1 is equal to 0.9 repeating. But when we know calculus, this is where we can bring out the heavy-duty weapon to figure out or to prove 0.9 repeating is equal to 1. So here's what I'd say we're going to look at. 0.99 repeating. Well, we know 0.99 repeating. If we go by our decimal place system, this is the tenths place. So it's 9/10 plus 9 100ths plus 9 1,000ths plus yada, yada, yada. It's an infinite series. Now look at this. I could write this as 9 times 1/10. I could write this as 9 times 1 100th. This is 9 times 1 1,000th plus yada, yada, yada. We could write this as, well, 1/10 is just, 1/10 to the first power. 1 100th, well, that's a 1/10 squared. 1 1,000th, that's a 1/10 cubed. It's a geometric series. In fact, it's the geometric series r times 1/10 to the n, and n starts at 1. So based on that last homework problem that I just did on the board, we know this is a geometric series. R is 1/10. That's less than 1. It converges, so it has a sum. But based on that last example, that last homework problem that I asked you to do, and we just did on the board, the formula for the sum of a geometric series gives you the sum when the starting value is 1. Well, the only difference If the starting value is 0, the first term of this series would be, well, 1/10 of the 0 is 1, would be 9. Then we would have 9 times 1/10 to the first, plus yada, yada, yada. So the only difference between this series, which we have the formula to find the sum of, and this series is that first term of 9. So I think we can use our formula, S equals A over 1 minus R, to get the sum of this series. So A is 9, R is 1/10. So it's a 9 over, 9/10? And 9 over 9/10 is 10. The sum of this series is 10. The sum of this series is found by just taking the sum of the series that starts at 0 and subtracting off the first term. So subtract off the first term. And you know what? I can put a hardcore equals there. The sum of this series, n equals 1 to infinity, 9 times 1/10 to the n, it has a sum of 1, which proves that this series, 0.9 repeating, equals 1. Alright, so we started our journey into the cataloging of infinite series. You now know what the importance of partial sums, and we did a couple of examples that involved that. Telescoping series. That was like our first one, and we saw telescoping, things collapse down. We still needed to use our knowledge of partial sums there. And then geometric series. So we've got to start. You know, we have two weapons in our toolkit, so to speak. We're going to end up with about 10 by the time we're done with this chapter. So, you know, at this time, you know, that's all there is in this section. So go attack the homework and do the homework. In section 10.3, do the homework. Thanks for watching.